question today is, what is the law of conservation of momentum? For anything to be conserved means that it stays the same. So the conservation momentum says that in the absence of an external force, the momentum of a system stays the same. An example of this here would be like firing off a cannon. So how is momentum conserved when firing a cannon? Well, before the cannon is fired, everything is just simply sitting there. It's at rest. So therefore, the momentum before the cannon is fired is zero. Both the cannonball and the cannon have a zero velocity, so the mass times the velocity, which is zero, must be zero as well. Now, for something to be conserved means that the momentum stays the same. So if the momentum before the cannon fires is zero, and momentum is conserved, that means the momentum after the cannon is fired is also zero. Well, how can that be? Well, the cannonball clearly has momentum because it has mass and it has velocity. And the cannon itself also has momentum because it has mass and it has velocity. But what happens is the cannonball has a positive momentum because it is moving forward, and the cannon has a negative momentum because it is moving backwards. And it turns out that they have the same amount of momentum, the same amount of positive as negative momentum, and therefore they cancel out. So after firing, the momentum of the cannon, which is the recoil, it is going to move backwards. Whenever you fire the cannon, it's going to move backwards. So the momentum of the cannon, which is the recoil, is equal and opposite to the momentum of the cannonball. In other words, they cancel each other out to make the total still be zero. Now, one thing I want to point out to you here, though, is that the momentum of the cannon here is mostly in the mass. It has a large amount of mass and a small velocity. And that is a negative momentum. The cannonball, however, has a small mass but a large velocity. And that is a positive momentum. So even though they have the same momentum, because the mass of the cannon is much larger, it has a smaller velocity. And because the cannonball has a smaller mass, it has most of its momentum in the velocity portion. And so therefore, there's less recoil the larger the mass of the cannon. So you want the cannon to be very heavy so it doesn't have as much recoil. Let's work through a problem here that illustrates this conservation momentum. So here we have a 63-kilogram astronaut who's on a spacewalk when the tether line to the shuttle breaks. So he has the space shuttle here. And there's usually a tether line, but unfortunately that tether line is broken, and so he starts to drift away. It says the astronaut is able to throw a 10-kilogram oxygen tank in the direction away from the shuttle with a speed of 12 meters per second, propelling the astronaut back to the shuttle. So he is going to essentially throw this oxygen tank forward to propel himself backwards. He's going to recoil just like that cannon does. We want to find the final speed of the astronaut. Now, they start together. So in the beginning, the astronaut is holding on to the tank, the oxygen tank. And so together, their mass is both the 63 and the 10. So they have, when you see here the total, they have a total of 63 plus 10, which is 73 kilograms. Then afterwards, they are separate. So after that throwing, they're going to separate. So let's say that this is the oxygen tank and this is the astronaut. The oxygen tank's mass is 10. And the astronaut's mass is 63. So here they are together, so we have the total mass. Here they are separate, and so we have just the mass of the oxygen tank and just the mass of the astronaut. Now let's look at those velocities. So we have a velocity of 12 meters per second, and that is going to be the velocity of the oxygen tank. The oxygen tank is thrown in the direction away from the shuttle with a speed of 12 meters per second. So that is the velocity of the oxygen tank, which is 12. But we can only have one unknown, so only one of these boxes can be unknown. And that one that we're trying to find is it's asking, find the final speed of the astronaut. So the astronaut, we're trying to find his or her final speed. That means that we already know the velocity when they are together. And when they are together, the astronaut and the oxygen tank are at rest. They are not moving. Their velocity is 0. So now we're going to solve here. And in order to solve, we're going to multiply these two together. 73 times 0, which is 0. We have an equal sign here. We're going to multiply these two together. 10 times 12 is 120. Then we have a plus sign. And then we're going to multiply these two together. Now, we don't know this number, so we're going to keep this as 63 times v. Now, in order to solve this formula, the first thing we have to do is we have to move everything without the variable to the other side. So this number doesn't have a variable. So we're going to move that to the other side. Now, currently, it is added to this value. So to get it to the other side, we're going to subtract 120 on both sides. That'll get us a negative 120 equals, here they cancel out, and we're left with 63 times v. Now the next step in algebra is to get rid of those things connected to it through multiplication or division. So we're going to get rid of the 63 connected to it, and because it's multiplied, we undo multiplication by dividing. So we're going to divide 63 on both sides. Here the 63 will cancel out, and we are left with just v on this side. On this side here, we have 120, negative 120, divided by 63, and we get negative 1.90. Now we do need a unit as well. This is a velocity that we're talking about. So all velocities have units of meters per second. I think it's the easiest way to solve these problems is first place the masses in their appropriate boxes and then go through and put in the velocities. Again, only one of the boxes should have a question mark in it. All the other boxes should have a number.